Emission nebulae. These are the nurseries, and they're on fire. Not literally, though it would be a better story if they were. What's actually happening is stranger. Young, brutally hot stars are pumping out so much ultraviolet radiation that they're ripping electrons off the surrounding hydrogen gas. That gas doesn't just sit there stripped, it glows. The Orion Nebula, 1,344 light years away, is the closest big example. A stellar nursery you can see with your naked eye, mistaken for a fuzzy star by anyone who hasn't looked twice. Inside it, roughly 700 stars are forming right now. Not formed. Forming, present tense, mid collapse, mid ignition. Here's the scale that should stop you. Orion spans about 24 light years across. Light, the fastest thing that exists, takes 24 years just to cross it. And it's one of thousands of emission nebulae scattered through the galaxy, each one a delivery room for suns. The Carina Nebula, 4 times larger and considerably more violent, hosts Eta Carinae, a star so unstable it's expected to detonate as a supernova at any point in the next 100,000 years. Cosmically, tomorrow. But here's the thing about that glow. The red you see in long exposure photographs isn't decoration. It's hydrogen alpha emission, a specific wavelength produced when a freed electron falls back into a hydrogen atom and drops to a particular energy level. Every emission nebula on every poster, every screensaver, every desktop background of a red and orange cosmic cloud, that's atomic physics happening on a scale of trillions of miles, photographed as art. The one fact that changes everything: these nebulae are eating themselves. The same radiation that makes them glow is also destroying them. Stellar winds and UV radiation from the newborn stars sculpt and erode the gas clouds that made those stars in the first place, carving out cavities, blowing away the raw material for the next generation. The pillars of creation inside the Eagle Nebula are a famous example of this. Towers of gas and dust being slowly boiled away by the very stars they gave birth to. Some estimates suggest the pillars may have already been partially destroyed by a supernova shockwave, and we're just now receiving the light that shows them intact. We might be looking at a photograph of something that no longer exists. Let that sink in. The nursery consumes itself to make the child. That's not poetry. That's just what hydrogen does under enough gravity and enough light. And the timeline is faster than most people assume. A cloud like this can go from cold, quiet gas to a fully lit nursery glowing with hundreds of new stars in as little as a few 100,000 years, a geological instant. Then, within a few million more, the most massive of those new stars will have lived their entire lives and died, and the whole structure will have moved on to something else entirely. Emission nebulae aren't just nurseries. They're nurseries on a clock, and the clock is always running faster than it looks. And buried inside nurseries exactly like this one, something even stranger is happening. Something so small, so fragile, that it's easy to miss inside all that glowing gas. Not every object here is a star yet. Some of them are still deciding what they'll become. Protoplanetary nebulae, Proplyds, for short, are the newborn planetary system still tangled in the placenta. A proplyd is a young star, freshly ignited, still wrapped in a disk of gas and dust left over from its own formation. The Hubble Space Telescope found over 150 of them crammed into the Orion Nebula alone, each one a flattened, glowing disk a few times the size of our solar system, being actively cooked and eroded by the radiation of nearby massive stars. Some proplyds lose so much material to that radiation, up to the mass of the Earth every few years, that astronomers estimate certain disks in Orion have only a few million years left before they're stripped down to nothing. Here's the twist that reframes the whole idea of a nursery. A proplyd isn't just where a star is born. It's where a planet is born at the exact same time, out of the exact same leftover material, dust grains colliding, sticking, growing, eventually clumping into the first rough seeds of worlds. Every planet in our own solar system, this one included, almost certainly passed through a stage that looked exactly like a proplyd roughly 4.6 billion years ago, glowing in some now vanished nebula. But here's the part that should genuinely bother you. Most proplyds don't survive to finish the job. Squeezed by radiation from nearby giant stars, The vast majority of protoplanetary disks in a region like Orion are evaporated before planets can fully assemble, meaning most attempts at building a solar system simply fail, dissolved back into gas before they ever get the chance. Ours didn't fail. That's not a guarantee. That's a coin flip that happened to land the right way 4.6 billion years ago, and here we are to talk about it. There's an unsettling symmetry hiding in that number, too. Orion alone holds over 150 Proplyds. Most of the galaxy stars are thought to form in clusters exactly like it. Multiply that pattern across the roughly 100 billion stars in the Milky Way, and you're left with an estimate that's almost too large to process. This galaxy alone may have hosted trillions of attempted solar systems since it formed, the overwhelming majority of them lost before a single planet finished forming. So even inside a single stellar nursery, some of the light isn't the raw glow of ionized hydrogen. Some of it is dust, catching light it didn't make itself. Reflection nebulae. If emission nebulae are the ones that glow, reflection nebulae are the ones that just look like they do. There's no ionization here, no hydrogen getting stripped and relit. Instead, a reflection nebula is dust, plain interstellar dust, sitting near a star that isn't quite hot enough to ionize gas, but is more than bright enough to scatter light off tiny particles, the same way headlights scatter light off fog. What you're seeing isn't the nebula's own energy. It's reflected starlight bounced off grains of dust, roughly the size of smoke particles. Here's the twist that surprises almost everyone. That blue color you associate with nebulae in half the photos you've ever seen of the Pleiades cluster, that's not because blue is a nebula color. It's because dust scatters shorter, bluer wavelengths of light more efficiently than longer red ones. The exact same physics that makes Earth's sky blue. The Pleiades reflection nebula, wrapped around the Seven Sisters star cluster 444 light years away, is essentially interstellar fog lit by an extremely powerful flashlight, and the resemblance was close enough that early photographers assumed the cluster was simply overexposed. But here's the part that should genuinely bother you. Reflection nebulae are temporary, not in cosmic terms, in almost human terms. As the star drifts relative to the dust cloud or the dust gets blown away by stellar winds, the reflection fades. Some reflection nebulae are thought to persist for only a few 100,000 years before the geometry that makes them visible falls apart. On the timescale of a galaxy, that's not long. That's barely a flicker. The Pleiades cluster itself is only around 100 million years old, and the dust it's currently passing through isn't even material it was born with. It's an unrelated cloud the cluster happens to be drifting through right now, a chance encounter lit up for a cosmic instant. So here's where it gets stranger. The dust doing all that scattering is largely made of carbon and silicates, the literal building blocks of rocky planets, of asteroids, of the elements sitting in your own body. You are looking, when you look at a reflection nebula, at unassembled planetary material temporarily catching starlight before physics does something else with it. There's a quieter category hiding inside this one, too. Some reflection nebulae surround stars that haven't fully ignited yet, dusty envelopes around protostars, still gathering mass, scattering light before the star at the center has even finished forming. In those cases, the reflection nebula isn't just decoration around a finished star. It's a veil over a birth still in progress, lit from the inside by something not yet fully awake. Not every dust cloud gets a star to light it up, though. Some clouds sit far enough from anything bright that they don't reflect. They don't emit, they just block dark nebulae. This is the nebula defined entirely by absence. A dark nebula produces no light of its own and reflects almost none. It's simply dense enough, dust and molecular gas packed tightly enough, to block the light of everything behind it. You don't see a dark nebula directly. You see a hole, a silhouette, a rip in the star field where the Milky Way should be continuous and isn't. The Coalsack Nebula, visible to the naked eye near the Southern Cross, has been noticed by cultures across the Southern Hemisphere for thousands of years, not as an object, but as a gap. Indigenous Australian astronomy incorporated it into the sky's mythology as the head of an emu, formed not from stars, but from the absence of them. Long before telescopes, people were mapping the universe by what wasn't there. Here's the number that reframes the whole category. Some dark nebulae, like the famous Horsehead Nebula, contain enough material to form thousands of stars. They're not empty regions, they're some of the densest matter in that part of the galaxy, dense enough to be nearly opaque across dozens of light years, with internal temperatures that can drop to just 10 degrees above absolute zero. Darkness here doesn't mean nothing. It means too much, packed too tight for light to pass through. But here's the fact that changes the category entirely. Dark nebulae aren't a permanent type, they're a phase. Given enough time and enough gravity, the same dense gas that blocks starlight will collapse under its own weight, heat up, and ignite, turning a dark nebula into the very thing it's currently obscuring: an emission nebula, a stellar nursery, a source of light instead of an absence of it. The Horsehead Nebula is doing exactly this right now, its edges being eroded and lit by the very star forming activity happening at its base. And in perhaps 5 million years, what we currently photograph as a shadow may photograph as a glow. The dark nebula, in other words, isn't the opposite of a nursery. It's a nursery before the lights turn on. Every emission nebula you've ever seen photographed was, at some earlier point in its history, indistinguishable from a dark one. A quiet, cold, invisible mass, patiently waiting for enough of itself to collapse. There's also a scale to these clouds that rarely makes it into the pretty pictures. Giant molecular clouds, the largest dark nebulae, can span hundreds of light years and contain enough raw material to build millions of stars the size of the sun. The entire visible structure of a galaxy's spiral arms is, in part, a map of where these dark clouds happen to be sitting, waiting their turn. So far, every nebula we've covered has been about birth, gas assembling into stars, into disks, into planets. But nebulae don't only mark beginnings. Some of the most spectacular ones in the sky mark the opposite. And the first kind of death nebula has one of the most misleading names in all of astronomy: planetary nebulae. Despite the name, these have nothing to do with planets. Nothing at all. The name is a fossil of bad 18th century telescopes. When William Herschel and other early observers looked at these glowing shells through low-resolution optics, the round, softly lit disks reminded them of the pale blue-green disk of Uranus. The name stuck. 2.5 centuries later, we're still stuck explaining that no, there are no planets involved. What's actually happening is a sun-like star dying, not explosively but gently, almost gracefully, compared to what's coming later in this list. When a star, roughly the mass of our own sun, exhausts its hydrogen fuel, it swells into a red giant, then sheds its outer layers into space in a slow motion exhale that can last tens of thousands of years. What's left behind at the center is a white dwarf, the exposed, superheated core of the former star, with a surface temperature that can exceed 100,000 degrees Celsius. That white dwarf's ultraviolet radiation ionizes the expelled gas shell, and it lights up, the same emission physics as a stellar nursery, except this time the light source is a corpse, not a cradle. Here's the number that should unsettle you. The sun will do this. In roughly 5 billion years, after it swells to a red giant large enough to swallow Mercury and Venus, it will shed its outer layers and become, briefly, a planetary nebula. The Helix Nebula, 650 light years away, is thought to look almost exactly like what our solar system's remains will look like, glowing softly for around 10,000 years before fading. 10,000 years. That's how long the light show lasts. And here's the part that should genuinely bother you. That's roughly the same span as all of recorded human civilization. If planetary nebulae could watch, ours would fade before it finished writing our story. But here's the twist inside the twist. Planetary nebulae aren't rare oddities. Every star with roughly the sun's mass, the overwhelming majority of stars in the galaxy, ends this way, which means planetary nebulae aren't the exception. They're the default death. The quiet, common, oddly beautiful way that most stars go. And the shapes these dying stars leave behind are far stranger than the name planetary ever suggests. Some, like the Ring Nebula, form clean, simple shells. Others, like the Cat's Eye Nebula, fracture into concentric rings, knots, and jets that suggest multiple ejection events rather than one smooth exhale. Evidence, some astronomers think, of an unseen companion star tugging the dying star's outflow into asymmetric shapes. Even in death, these stars rarely go quietly or simply, they go elaborately, drawing structures in gas that no artist would have guessed a physics equation could produce. Not all stars get that peaceful an ending, though. The bigger ones don't fade, they detonate. Supernova remnants. This is what's left after a massive star doesn't fade quietly. It explodes with more energy than the sun will produce in its entire 10 billion year lifetime, released in seconds. When a star roughly 8 times the sun's mass or larger runs out of fuel, its core collapses in less than a second, then rebounds in a shockwave that tears the rest of the star apart. What remains isn't a slow shed shell like a planetary nebula. It's a debris field, expanding outward at speeds that can exceed 10,000 kilometers per second, fast enough to cross the distance from Earth to the moon in under 40 seconds. The Crab Nebula is the textbook case, and the dates attached to it are almost absurdly precise. Chinese and Arab astronomers recorded the supernova that created it in the year 1054, a guest star bright enough to be visible in daylight for 23 days. Nearly 1,000 years later, the debris is still expanding, still visible, still glowing, not from starlight reflection, but from synchrotron radiation, electrons spiraling at close to the speed of light around the magnetic field of the collapsed core at its center. A neutron star spinning 30 times per second, roughly the size of a city, containing more mass than the sun. Here's the fact that changes everything about this category. Supernova remnants aren't just spectacular wreckage, they're forges. The extreme pressures and temperatures of the explosion itself are one of the only places in the universe capable of producing elements heavier than iron, gold, silver, platinum, uranium. Every gold atom on Earth, in every ring, every circuit board, every filling in your teeth was forged in an explosion like this one, then scattered across space, then reassembled billions of years later into a planet, and then into you. Let that sink in. You are, by mass, partly made of stellar wreckage. Not metaphorically, chemically. And the remnants don't stay tidy forever either. Over tens of thousands of years, a supernova remnant slows, cools, and eventually merges back into the surrounding interstellar medium, dispersing the very heavy elements it forged into the next generation of dark nebulae, the next generation of Proplyds, the next generation of planets. Destruction here is just delivery with extra steps. There's a stranger, rarer category of exploding star, though, one that doesn't wait for the star to die a normal death at all. Some stars start shedding themselves violently while they're still burning. Wolf-Rayet nebulae. These belong to stars so massive and so hot that they're actively blasting themselves apart right now, decades before they ever explode. A Wolf-Rayet star is what's left when a star of roughly 20 solar masses or more burns so intensely that its own stellar wind, the outward pressure of light and particles, becomes strong enough to strip away its outer hydrogen layers while the star is still alive. These winds move at speeds up to 2,000 kilometers per second, carrying away the mass equivalent of the sun every 10,000 years or so. That's an almost incomprehensible rate of self-destruction, sustained for the final few 100,000 years of the star's life. A blink, even by the standards of this list. The result, when that fast wind slams into gas the star shed earlier in its life, is a nebula shaped less like a soft cloud and more like a shockwave frozen in place, bubbles, rings, and knotted filaments. The Crescent Nebula, formed by the Wolf-Rayet star WR 136, is a textbook case. An asymmetric bubble roughly 25 light years across, carved by collision after collision of stellar wind slamming into older, slower moving gas. Here's the twist. Wolf-Rayet stars are essentially previewing their own supernova while they're still alive. They're so massive that when they do finally collapse, and it happens fast within a few 100,000 years, a rounding error in stellar lifespans, the resulting explosion detonates into gas the star already partially cleared away, sometimes producing a stripped unvolute supernova that behaves differently from a standard explosion because so much of the star's outer material is already gone, already scattered, already a nebula in its own right, sometimes even collapsing directly into a black hole with barely a visible flash at all. So the star doesn't just die once. It sheds itself in advance, then dies into the wreckage of its own preparation. Nothing else in this list rehearses its own death quite like that. Wolf-Rayet stars are also rare in a way that makes them feel almost like a warning sign. Astronomers estimate only a few hundred exist in the entire Milky Way at any given time, precisely because the phase is so short and so extreme. Spotting one is less like finding a common type of star and more like catching a fuse mid-burn, which brings us to the full shape of the category. Every nebula in this video sorts into one of two stories, and the split is almost too clean to be an accident. On one side, birth, emission nebulae, protoplanetary proplyds, reflection nebulae, and dark nebulae are all in different ways gas and dust, either actively forming stars and planets or waiting to. One glows from ionization. One is a disk being carved into worlds. One glows from borrowed starlight. One doesn't glow at all, but all four are cradles at different stages of the same process, separated mostly by how close they are to actually lighting up, or how much of themselves they've already lost to the radiation around them. On the other side, death. Planetary nebulae are the gentle exhale of an average star, the fate waiting for our own sun in roughly 5 billion years. Supernova remnants are the violent detonation of a massive one, forging the heavy elements that birthside nebulae will eventually recycle into new planets. Wolf-Rayet nebulae are the strange in-between, a massive star shedding itself alive, rehearsing its own ending before it happens. 7 types, 2 stories. Birth and death, running on a loop that's been repeating since the first stars ignited roughly 13.6 billion years ago, and that will keep repeating long after every star alive today has finished its own turn through this list. Here's the part that should genuinely bother you. One more time, on the way out. Every element heavier than hydrogen and helium in your body, the carbon, the oxygen, the iron in your blood, the calcium in your bones, pass through at least one of these categories. Formed in a dying star, scattered by an explosion, gathered by gravity into a dark nebula, spun into a Proplyds disk, collapsed into a new star and its planets, and eventually into you. You are not just observing this cycle. You are a byproduct of it, temporarily arranged on a rock looking up. Not bad for stick figures on a rock.